Thank you everybody for coming to my doctoral dissertation. Today I would like to give a lecture entitled Chemistry of N-heterocyclic carbenes with selected fluoride sources. If you take a look at the overview, first we're going to define the fundamental problem that prompted this research. Then we're going to see reactivity of N-heterocyclic carbenes with antimony trifluoride. In the second part, we're going to take a look on reactivity of N-heterocyclic carbene with different HF sources and how we managed to derive a new naked fluoride reagent from this research. And we will, in the end, we will test the reagent's reactivity. So, if we begin, the problem with metal fluorides is they tend to form long polymer chains that have high lattice energies, and that renders them insoluble, especially in non-polar solvents. Consequently, they have decreased applicability, and we wanted to address this issue. And how would one go about doing this? Well, we thought, why don't we try and to coordinate to the metal a large organic ligand, which would then prevent the formation of polymer chains and afford monomeric units that would be soluble in non-polar solvents. And we envision two possible approaches. And the first one is direct reaction of N-heterocyclic carbene with metal fluoride that would yield the desired complex. Or in the second one, to prepare different N-heterocyclic carbene coordinated metal complexes with different leaving groups, and then try and perform substitution of these leaving groups with fluoride ligands. So let's see what we found out. First, direct reactions were attempted with different first row D block metal fluorides in different oxidation states. However, all of these reactions gave negative results. And this brings me to part one, the reactivity of N-heterocyclic carbene with antimony trifluoride. Because all the initial reactions gave negative results, we said, why don't we use a metal substrate, a fluoride substrate that is at least sparingly soluble, and try to learn from this system. And for the first reaction, we tried to mix it with carbene in tetrahydrofuran as a polar aprotic solvent, and the reaction yielded a new type of imidazolium salt. We managed to fully characterize it, and although this is a side product, we managed to draw two important conclusions from this one. The first is that the source of the protons responsible for imidazolium cation formation are solvent molecules, and second, all three imidazolium protons are highly labile and can easily undergo a hydrogen-deuterium exchange. Now, because polar solvents can favor ionic products, we said, why don't we try to perform the reaction in toluene. However, even at prolonged reaction times under harsh reaction conditions, no reaction was observed, and this was attributed to negligible solubility of antimony trifluoride in toluene. Nevertheless, you can do a little trick. That is, literature findings report that antimony trifluoride can easily be complexed with different amino, phosphino, or ether ligands and form complexes. For that purpose, we chose tetramethylethylenediamine ligand, which gave us the product in quantitative yields. We managed to fully characterize it, and here I would just like to say that this complex has profound solubility in toluene, so it can be used as antimony trifluoride syntone in non-polar solvents. And we did the next reaction. We took our complex and mixed it with carbene, hopefully that the carbene would displace the amino ligand and form a neutral product that we were searching. But that didn't happen. What happened is we got such a product. So again, an ionic product, but if you take a closer look, this one is a bit special. And you can see that it represents autoionization product of antimony 3 fluoride. Namely, two SbF3 molecules form SbF2 plus and SbF4 minus ions. We've also managed to characterize it with crystal structure analysis, and from it you can see that one of the carbenes binds to SbF2 moiety normally via C2 position. However, the second one binds abnormally via C4 position, and this complex represents the first example of abnormally bound carbene on any metal or metalloid fluoride up to date. But the formation of this product opened more questions than it solved. Namely, we wanted to know what is the mechanism of this conversion. We just knew the input and the output we got in the solid, but we didn't know what's happening in the solution. And more directly, we wanted to know if this auxiliary ligand that helped us with solubility is responsible for such transformation. And we wanted to test this, and we said, why don't we, instead of the main ligand, use dimethoxyethane? It is also a coordinating ligand, and when we did this reaction, the reaction got us the same result. And then we were wondering, are both or neither responsible for autoionization product formation? And the meta was suggested in previous research that it acts as a base. In some point during the mechanism it gets protonated and then deprotonated again. But if that would be true, in the case of dimethoxyethane, if ethers get protonated, we could expect CO bond cleavage. So in the reaction mixture, we would maybe have to observe some hydrolysis product of dimethoxyethane. That's why we decided to perform all of these reactions in deuterated solvents and observe the reaction mixtures with NMR. And in the NMR spectra, what we could see is we only have 3 uncoordinated dimethoxyethane and thymine ligands. Moreover, in the case of dimethoxyethane, no hydrolysis product or anything else was observed. From the methyl protons of carbene ligand, for both reactions we observed the same trend, and that is magnetic unequivalence of these protons got bigger. And this trend was observed for both reactions. From that we concluded that in the solution the auxiliary ligands are displaced and we get a neutral coordination compound. Then with a bit of research and creativity we could easily find a logical mechanism and propose it how the formation of our product goes. And to our luck and excitement, although the proposed mechanism, it was additionally substantiated by the researchers from Oxford in another Dalton transaction paper a few months ago. So, if we recap this first part, we described the synthesis and characterization of rare SbF2 plus cation. We concluded that N-heterocyclic carbene causes antimony 3 fluoride autoionization process. The autoionization product features first mesoionic and heterocyclic carbene rearrangement on any metal or metalloid fluoride to date. We performed mechanistic studies. We showed that structural analysis is in full accordance with valence shell electron pair repulsion model, and we successfully used antimony 3 fluoride thymine reagent that represents a soluble antimony 3 fluoride synton in nonpolar solvents. After a good year of trying to solve this antimony problem, we decided, well, if we would get by direct reaction a metal substrate that would give us a positive result, that would be an exception rather than a rule. And that's why we wanted to put our focus into the second mechanism. And for the second mechanism, we had to find a suitable and compatible fluoride source that would achieve this transformation. And We returned to the literature in hopes that we would find how to realize this idea. And when I was doing the research, I stumbled upon this reaction. So you can take two imidazolium chlorides, react it with silver oxide, and with the elimination of water, you get soluble silver chloride. Now, PhD students, when he writes this equation down on a paper, can easily solve the problem. You cross out chlorides, replace them with fluorides, and there you go. But the real problem was now how to prepare pure and anhydrous imidazolium chloride. And this brings me to part 2, reactivity of N-heterocyclic carbenes with different HF sources. Now, imidazolium fluoride falls into the category of naked fluoride reagents. Here is the family of known naked fluoride reagents with its beneficial or wanted properties. Now, I don't have time to go into details about their properties. However, it suffices to say, to the best of my knowledge, I haven't been able to find a single example of a naked fluoride reagent that would be chemically stable, at least in acetonitrile. And significant advances are to be made in their anhydrous synthesis. And I'll tell you why. The general synthesis procedure of all of this is that you take a different halide salt, namely chloride, bromide, and iodine, and then perform a metathetic or substitution reaction with different metal fluorides, mostly alkali metal fluorides. And this brings us to the problem which I'm talking about throughout this lecture. Alkali metal fluorides are scarcely soluble in solvents. That's why you have to perform this reaction in the presence of water. But you don't want to do that. And you don't want to do that because reactivity of fluoride anion is highly dependent on its environment. And water usually deactivates and changes its reactivity, and you don't want it to be present in the reaction mixture. Moreover, by doing substitution reaction, you get, of course, your product, but with it another MX salt. And the research on this field showed that purification and isolation of anhydrous imidazolium fluoride product is difficult. And what we envisioned is, well, we have imidazolium chloride, but then we said we're not going with the metathetical mechanism. Why don't we go by established synthesis procedure to N-heterocyclic carbene and then try to perform addition of hydrogen fluoride to the carbene? And I took carbene and mixed it with anhydrous hydrogen fluoride, which acted as a solvent and as a reagent. And I just hoped it doesn't destroy my substrate, it doesn't react differently, or it doesn't burn it. Luckily, it didn't, but it didn't give me imidazolium fluoride either. What it gave me is imidazolium polyhydrogen fluoride. And we managed to fully characterize this product, and here I would like to note this is not a fluoride reagent because these two HF molecules can get dissociated, so this is an acidic reagent or HF reagent. But we were kind of on the right way because if with surplus or 3 equivalents the reaction yields polyhydrogen fluoride, then the question arose, can we then by stoichiometric quantities with 2 equivalents get bifluoride anion and finally with 1 our wanted reagent? And then we had to solve the problem of anhydrous hydrogen fluoride, and we successfully find its replacement, which is 3-ethylamine 3-hydrogen fluoride complex, which is just a milder version. And when I repeated the reaction with surplus of this one, the reaction gave me the same result, and that made me rather happy. And luckily then with 2 equivalents I got my bifluoride product, and finally with 1 my wanted imidazolium fluoride reagent. Here are the crystal structures that are also interesting for several reasons, and I don't have time to go into it. And here we can see our fluoride anion loosely stabilized by 4 hydrogen bonds in a crystal structure. But the interesting thing starts to happen not in crystal structure but in solution. That's why I would like to show you superimposed spectra of all three anions. On the far right, we get dihydrogen 3 fluoride. On the opposite scale, we get a characteristic doublet signal for bifluoride anion, and almost at the same chemical shift, we get a singlet peak for imidazolium fluoride. Now, why am I showing you this? I'm showing you this because I've grown monocrystals of imidazolium fluoride. I took it to X-ray analysis, got parameters for the crystal cell and everything, and then dissolved the crystals in deuterated acetonitrile. And when I took this sample on NMR analysis, it showed me this peak. And this is confusing and strange because this peak corresponds to bifluoride anion. And this set us back for about 3 weeks or almost a month. And a valuable lesson was learned that sometimes you have to be patient with chemistry and you just have to wait a little bit. Because if you leave this sample standing for another day or so, the doublet peak is gone, and again a singlet peak characteristic for imidazolium fluoride can be observed. But do you know what this means? This means that two imidazolium fluorides in acetonitrile, they react and form bifluoride and free carbene moiety as a kinetically controlled products. And with time, reaction goes back and thermodynamically more stable imidazolium fluoride forms. Which, if you think, is rather interesting. Two imidazolium salts form free carbene molecule. This type of chemistry hasn't been observed before. If we now take a look at the whole reaction scheme overview, we said, well, if one transforms into two and back, we said, of course, if we prepare pure bifluoride compound and react it with additional equivalent of carbene, would that go to monofluoride product? And of course, the answer was yes. But then we thought, well, we know one bifluoride molecule that is not dangerous, it's not harmful, it's stable on air, it's widely used in industrial level and really cheap, and that is potassium bifluoride. And we thought, what if we react carbene with potassium bifluoride? And the reaction got us the same result. So now we had a really elegant and easy way how to prepare analytically pure anhydrous imidazolium fluoride on a gram scale. And if I just briefly return to the beneficial properties, we see that we managed to derive a simple anhydrous synthesis of our product, and most importantly, we show that it's thermodynamically stable in acetonitrile. And these last two check boxes are actually the added value here in the field of naked fluoride reagents. So if we go run through, so we derived anhydrous synthesis of a novel naked fluoride reagent. We additionally synthesized two other polyhydrogen fluoride salts. All three were synthesized using different sources of HF, which demonstrates the versatility of the applied synthetic approach. And all three were isolated in high yields and high purity. And this brings me to part 3. Although we've managed to find an elegant synthetic way, and we show that the product has beneficial properties such as solubility and stability, that means nothing if not for wanted reactivity. And we set ourselves to test its reactivity. And how we did that, we took imidazolium fluoride and reacted it with metal tetrafluorides, namely silicon tetrafluoride and germanium tetrafluoride, to obtain discrete Trigonal-Bipyramidal pentafluoridogermanate and pentafluoridogermanate anions respectively. And then you can take the formed product, react it with additional equivalent of the reagent, and the reaction yielded us hexafluoridogermanate anion. Now, here are the crystal structures. This is pentafluoridosilicate anion. This one is not as interesting because there are about a dozen such structural motifs reported in the literature. However, this is the first example of structural characterization of pentafluoridogermanate anion. And I would like to spend the last minutes to talk about the surprising fact that we managed to stabilize and crystallize this product. If you think about it, the chemistry is not that hard, really, and it's not like we are the first that tried this. There were several reports that tried to perform such a reaction with different fluoride sources, but none of them achieved the isolation of discrete Trigonal-Bipyramidal pentafluoridogermanate anion. And if we take a look at the crystal structure, we can see that metal halides tend to form hexahalidometallate anions, and pentahalidometallate anions represent only roughly 10% of all the structures. And we were wondering why. And in the literature you can find and perform calculations. So for example, you can calculate, if you want addition of one fluoride to, let's say, germanium tetrafluoride to yield pentafluoridogermanate anion. And if you then calculate the total energy of this system, you see that the product is favored against the reactants by roughly 340 kilojoules per mole. And you can then calculate the next step, so addition of another fluoride to pentafluoridogermanate anion to form hexafluoridogermanate anion. However, if you take a look, this one is disfavored to the reactants. And so this model does not appropriately address the empirical data and the observed structures. And then we turned for help to a brilliant mind of Tone Kokalj, and he said, of course this is so. These are isolated anions, and germanium as a small object can hardly accommodate a large surplus of electron density. But in reality, these anions are never alone. They are always surrounded with cations for the purpose of charge neutrality. And we said, why don't we devise a new, different theoretical model where we have all molecular species. So we have molecular sodium fluoride, germanium tetrafluoride, and the corresponding products. And if you then perform calculations on this system, you can see that they reflect the observed structure, the empirical data. Namely, the first product, so sodium pentafluoridogermanate, is favored against the reactants by roughly 180 kilojoules per mole. However, the next reaction step is even more favorable. And although these numbers are not to be taken too absolutely, it was the trend that we were interested in. So now we had a model that shows us the state of nature, and what you can do with this model then is you can change it with different cations. You get different values, and you can then deduct these values to get a difference. And this difference now gives you information how much is pentafluoridogermanate favored or disfavored against the hexafluoridogermanate. And we did this. You already see the numbers for sodium cation. The difference comes to minus 63 kilojoules per mole, and we collect the number. We did then the same for ammonium cation, which is slightly bigger, and collect the number, and in the final step we did this for tetramethylammonium cation. And now we have some absolute numbers that again don't tell us much, but what you can do with these numbers is you can plot them as a function of the distance between center of charge of the cation and center of charge of the anion. And if you do this, you can see sodium as a really small cation can get really close to the anion, and the energy difference is quite negative. Ammonium, slightly bigger, cannot get as close. The energy difference decreases a little bit, and in the case of tetramethylammonium cation, it comes up to the positive values. So now what this tells us is that thermodynamic preference of hexafluoridogermanate against pentafluoridogermanate diminishes with increasing size of the cation. In other words, small cations can effectively stabilize more electron density on a given moiety via electrostatic Coulomb interactions. And here a PhD student asks himself, aren't there a lot of systems that are driven by electrostatic interactions? And so the question here arises, how could these results be viewed or expanded to biological system, drug design, design of materials, self-assembly, etc. All systems that are heavily driven by non-covalent interactions. And we're not saying that in our case this is absolutely true, because right now we don't have, we have no way of knowing. But it may as well be that the specific bulkiness, the specific characteristics and geometric properties and electronic properties of our cation increased the crystallinity in our product that enable us first structural characterization of pentafluoridogermanate anion. And I would like to conclude this part 3, that we showed successful reactivity of our novel reagent. We isolated discrete Trigonal-Bipyramidal anions. We showed the first structural characterization of pentafluoridogermanate anion and devised a new theoretical model for relative stability assessment of pentafluoridogermanate versus hexafluoridogermanate structural motifs. And this brings me to today. Well, I've set on a journey to prepare soluble metal fluorides. However, I fell short of this goal because of the time constraints. But we did manage to achieve something that I wanted since day one I set foot in this institution, and that is to leave something useful behind. And with this reagent, not only can we immediately now try and perform this mechanism, we can also use it in dozens of other that were maybe unachievable before, maybe due to shortcomings, solubility shortcomings of the reagent, or stability shortcomings of the reagent, or maybe specific steric or electronic properties. And I would like to conclude with this thought. At the end, thank you to everybody that participated in this research. Great thanks goes to Gaspar, my mentor. Of course, the co-authors Tone and Melita and Alič, our analytical duo Maya and Mira for the performed chemical analysis. The research wouldn't be the same without Matic and Christian, so thank you guys for everything. Of course, Evgeny for all the help with crystallography, and Robert, who taught me how to handle nickel vacuum line and helped with the fluoride gases. To the rest of my colleagues, even those who moved out of my office, and actually to everybody who shared this 4-year and 24 days long experience with me. Thank you all.